In this video lecture, we are going to discuss the working principle of the different types of AC voltage controllers. If a thyristor switch is connected between AC supply and load, the power flow can be controlled by varying the RMS value of AC voltage applied to the load, and this type of power circuit is known as an AC voltage controller. So the most common applications of AC voltage controllers are industrial heating, on-load transformer tap changing, light controls, speed control of polyphase induction motors, and AC magnet controls. For power transfer, two types of control are normally used, that is the on-off control and the phase angle control. So in on-off control, the thyristor switches connect to the load to the AC source for a few cycles of input voltage and then disconnect it for another few cycles. In phase control, thyristor switches connect the load to the AC source for a portion of each cycle of input voltage. The AC voltage controllers can be classified into two types: single phase controllers and three-phase controllers. Each type can be subdivided into unidirectional or half-wave control and bidirectional or full-wave control. There are various configurations of three-phase controllers depending on the connections of thyristor switches. Since the input voltage is AC, thyristors are line commutated, and phase control thyristors, which are relatively inexpensive and slower than fast switching thyristors, are normally used. For applications up to 400 Hz, if triacs are available to meet the voltage and current ratings of a particular application, triacs are most commonly used. Further, due to line or natural commutation, there is no need of extra commutation circuitry, and the circuits for AC voltage controllers are very simple. So let us discuss the single phase full wave controllers with a resistive load. So you can see here the figure of a single phase full wave controller with a resistive load connected. So during the positive half cycle of input voltage, the power flow is controlled by varying the delay angle of thyristor T1, and thyristor T2 controls the power flow during the negative half cycle of input voltage. So the firing pulses of T1 and T2 are kept 180 degrees apart. Further, you can see the waveforms for the input voltage, the output voltage, and gate signals for T1 and T2. If Vs is equal to under root 2 Vs sine omega t is the input voltage, and the delay angles of thyristor T1 and T2 are equal, that is alpha 1 is equal to alpha 2 is equal to alpha, the average value of the RMS value of the output voltage can be found from the given equation. V0 that is equal to under root of 2 upon 2 pi integration of alpha to pi 2 Vs square sine square omega t d omega t, which comes out to be Vs under root of 1 upon pi minus alpha plus sine 2 alpha upon 2. So by varying alpha from 0 to pi, V0 can be varied from Vs to 0. The gating circuits for thyristors T1 and T2 must be isolated. It is possible to have a common cathode for T1 and T2 by adding two diodes. Across the two thyristors. So as diode D1 is connected across T2 and diode D2 is connected across T1. So the thyristor T1 and diode D1 conduct together during the positive half cycle, and thyristor T2 and diode D2 conduct during the negative half cycle. Since this circuit can have a communal terminal for gating signals of T1 and T2, only one isolation circuit is required, but at the expense of two power diodes. Due to two power devices conducting at the same time, the conduction losses of devices would increase and the efficiency would be reduced. Further, in this particular figure, we can see the single phase full wave controller with an inductive load. So instead of the load R, we can see the load is RL in this particular figure. So in practice, most of the loads are inductive to a certain extent. Let us assume that thyristor T1 is fired during the positive half cycle and carries the load current. Due to inductance in the circuit, the current of thyristor T1 would not fall to 0 at omega t is equal to pi when the input voltage starts to be negative. Thyristor T1 will continue to conduct until its current I1 falls to 0 at omega t is equal to beta. The conduction angle of thyristor T1 is equal to delta, that is equal to beta minus alpha, and depends on the delay angle alpha and the power factor angle of load theta. So the waveforms for the thyristor current, the gating pulses and the input voltage can be seen in this figure. The angle beta, which is also known as an extension angle, can be determined from the transcendental equation, and it requires an iterative method of solution. Once beta is known, the conduction angle alpha of thyristor T1 can be found from delta is equal to beta minus alpha. Calculating the RMS value of output voltage, it becomes V0 is equal to under root of 2 upon 2 pi integration of alpha to beta 2 Vs square sine square omega t d omega t. This on derivation comes out to be equal to Vs under root of 1 upon pi beta minus alpha plus sine 2 alpha upon 2 minus 2 beta upon 2. The gating signals of thyristors should be short pulses for a controller with resistive loads. However, such short pulses are not suitable for inductive loads. The circuit diagram in this figure is of a three-phase full-wave bidirectional controller with a Y-connected resistive load. The operation of this controller is similar to that of a half-wave controller. So here you can see 6 thyristors T1, T2, T3, T4, T5 and T6 are connected here. So if we define the instantaneous input phase voltages as VAN is equal to under root 2 Vs sine omega t, VBN is equal to under root 2 Vs sine omega t minus 2 pi by 3, VCN is equal to under root 2 Vs sine omega t minus 4 pi by 3. The instantaneous input line voltages are VAB, that is equal to under root 6 Vs sine omega t plus pi by 6, VBC is equal to under root 6 Vs sine omega t minus pi by 2, VCA, that is equal to under root 6 Vs sine omega t minus 7 pi by 6. The waveforms for the input voltages, conduction angle of thyristors, and output phase voltages are shown in this figure for alpha is equal to 60 degrees and for alpha is equal to 120 degrees. So for alpha greater than 0 less than 60 degrees, immediately before the firing of T1, two thyristors conduct. Once T1 is fired, three thyristors conduct. A thyristor turns off when its current attempts to reverse. The conditions alternate between 2 and 3 conducting thyristors. For alpha greater than 60 degrees and less than 90 degrees, only two thyristors conduct at any time. For alpha greater than equal to 90 degrees and less than 150 degrees, although two thyristors conduct at any time, there are periods when no thyristors are on. For alpha greater than equal to 150 degrees, there is no period for two conducting thyristors and the output voltage becomes 0 at alpha is equal to 150 degrees. So the range of delay angle is alpha greater than equal to 0 degrees less than equal to 150 degrees. The expression for the RMS output phase voltage depends on the range of delay angles. The RMS output voltage for a Y-connected load can be found as follows. For alpha in between 0 degrees and 60 degrees, V0 is equal to under root of 1 upon 2 pi integration of 0 to 2 pi VAN square d omega t. Substituting the values of VAN and putting the limits, you get under root 6 Vs. In brackets, it is 2 upon 2 pi integration of alpha to pi by 3 sine square omega t divided by 3 d omega t plus integration of pi by 4 to pi by 2 plus alpha sine square omega t upon 4 d omega t. This comes out to be equal to under root 6 Vs under root of 1 upon pi in brackets pi minus 6 minus alpha by 4 plus sine 2 alpha upon 8. For alpha greater than equal to 60 degrees and less than 90 degrees, the value of V0 on substituting the value of voltage, we get under root 6 Vs under root of 1 upon pi by 12 plus 3 sine 2 alpha upon 16 plus under root 3 cos 2 alpha upon 16. For alpha greater than equal to 90 degrees and less than equal to 150 degrees, it comes out to be root 6 Vs under root of 1 upon pi in brackets 5 pi upon 24 minus alpha upon 4 plus sine 2 alpha upon 16 plus under root 3 cos 2 alpha upon 16. So if the terminals of a three-phase system are accessible, the control elements and the load may be connected in delta as shown in this figure. Since the phase current in a normal three-phase system is only 1 upon under root 3 times of the line current, the current ratings of thyristors would be less than that if thyristors were placed in the line. Let us assume that the instantaneous line-to-line voltages are VAB is equal to under root 2 Vs sin omega t, VBC is equal to under root 2 Vs sin omega t minus 2 pi by 3, VCA is equal to under root 2 Vs sin omega t minus 4 pi by 3. The line voltages, the phase and the line currents and thyristor gating signals are shown in this figure for alpha is equal to 120 degrees and a resistive load. So we can see in this particular figure the waveforms being shown are the input line voltages, the thyristor gate pulses, the output phase currents, and output line currents. For resistive load, the RMS output voltage can be determined from the relation V0 is equal to under root of 1 upon 2 pi integration of alpha to 2 pi BAB square T omega T, which comes out to be equal to Vs under root of 1 upon pi minus alpha plus sine 2 alpha upon 2. So the maximum output voltage would be obtained when alpha is equal to 0 and the control angle of delay angle is alpha greater than 0 less than pi. So in this lecture we discussed the different types of phase control and we discussed the working principle of single phase full wave controllers with rectifier loads, single phase full wave controllers with inductive loads, three phase full wave controllers and three phase full wave delta connected controllers. Thank you for going through this video lecture patiently. Thank you.